This is the video on saltatory conduction. Our nerves are responsible for transmitting all of the data from external and internal stimuli. This transmission process needs to be achieved incredibly rapidly, so it's a good thing our nerves are myelinated. Saltatory conduction comes from the Latin word saltare, meaning to leap. It is used to describe how the action potential leaps down myelin-coated axons. The myelin sheath, made up of oligodendrocytes in the central nervous system and Schwann cells in the peripheral nervous system, insulates the axon with its layers of glial membranes. An action potential typically travels down the entire length of an axon by depolarizing the membrane. This is achieved through the opening and closing of sodium and potassium channels. The myelin sheath inhibits the propagation of electrochemical signals at those locations since there are no channels under the myelin. The signals are therefore forced to seek out the next available gate for depolarization. These gates only occur at gaps in the myelin, called the nodes of Ranvier. By leaping to the next node, the signal travels much faster on the myelinated axons compared to the unmyelinated ones. For example, in A-alpha motor neurons, which are myelinated, the conduction velocity is between 80 and 120 meters per second. In C-type sensory axons, however, conduction velocity is only 0.5 to 2 meters per second, as they are unmyelinated pain fibers. This is why you can drop a rock on your toe and it takes a second or two before you fully feel the effects. Saltatory conduction is necessary for many of our neural processes, which is why the loss or degeneration of myelin can cause so many problems. In multiple sclerosis, the immune system attacks the myelin in the brain, so action potentials can't fire properly. This can result in numbness, weakness, problems with speech and thought, impaired movement of the limbs, and even paralysis. This ends the video on saltatory conduction.